Today we are going to learn about mastering instruction tuning with FLAN T0. In this video, we will dive into setting up and executing instruction tuning with FLAN T0 to enhance model performance across various tasks, equipping you with essential skills for AI advancements. Welcome to our educational journey on mastering instruction tuning with FLAN T0. Instruction tuning is a vital process in enhancing AI models' performance across various tasks. In this video, we will explore how you can effectively implement and scale instruction tuning using FLAN T0. We'll begin with an introduction to instruction tuning and its significance, followed by a detailed overview of the FLAN T0 architecture. As we progress, you'll learn how to set up and execute instruction tuning, create effective instruction sets, and evaluate improvements in model performance. We'll also tackle common troubleshooting issues and discuss scaling techniques for large datasets. Finally, we'll touch on future directions and advancements in instruction tuning. By the end of this video, you will have the skills necessary to apply instruction tuning effectively in your AI projects. Let's get started. Instruction tuning is a technique used to improve the performance of AI models by refining how they interpret and execute tasks. Unlike traditional tuning methods that focus solely on adjusting model parameters, instruction tuning involves modifying the instructions or prompts given to a model, enhancing its understanding and execution of tasks. This process is crucial as it allows for more nuanced and contextually aware AI responses, ultimately leading to better performance across a variety of tasks. Instruction tuning can be compared to teaching a student not just the content of a subject, but how to approach solving problems within that subject. The benefits of instruction tuning are numerous. It allows models to perform better on unseen tasks, improves their generalization capabilities, and can significantly reduce the amount of data required for training, making AI development more efficient and scalable. Successful applications of instruction tuning can be seen in areas like natural language processing, where it has led to significant improvements in tasks such as sentiment analysis, translation, and question answering systems. FLAN T0 is an advanced architecture designed specifically to enhance instruction tuning processes. It stands out due to its unique ability to process and execute complex instructions with greater efficiency and accuracy. At its core, FLAN T0 integrates several cutting-edge components that allow it to handle diverse and challenging tasks. These components include a sophisticated attention mechanism that improves focus on relevant parts of the input data, a robust understanding of context, and an enhanced capacity for learning from minimal data. One of the unique features of FLAN T0 is its ability to dynamically adapt to different tasks without requiring a complete retraining for each new task. This adaptability makes it particularly valuable in environments where tasks frequently change, or data availability is limited. Compared to other architectures, FLAN T0 offers superior performance in terms of speed and accuracy, largely due to its optimized instruction processing capabilities. It's particularly well suited for applications in natural language processing, automated reasoning, and other AI fields where understanding and executing complex instructions is crucial. Setting up FLAN T0 requires attention to both hardware and software components to ensure optimal performance. Firstly, it's important to have a compatible computing environment. FLAN T0 can benefit from GPUs for faster processing, so a setup with a modern GPU is recommended. On the software side, ensure you have the latest versions of Python and relevant libraries such as TensorFlow or PyTorch, depending on your preference. The installation process begins with downloading the FLAN T0 package from the official repository. Follow the installation instructions provided, which typically involve setting up a virtual environment and installing dependencies. Once installed, configuration is key to maximizing performance. Configure your environment to allocate sufficient resources to the FLAN T0 process, especially memory and processing power. During setup, you might encounter challenges such as dependency conflicts or installation errors. These can usually be resolved by ensuring all software components are up to date and compatible. To ensure optimal performance, it's also advisable to perform a series of test runs on sample tasks, tweaking configurations as needed to achieve the best results. Creating effective instruction sets is a cornerstone of successful instruction tuning. An instruction set can be likened to a recipe that the model follows to perform a task. The clarity and precision of these instructions directly influence the model's performance. To craft effective instructions, begin by defining the task clearly. Use straightforward language and avoid ambiguity, ensuring the model understands what is expected. Techniques such as using examples or analogies can help clarify complex tasks. It's also beneficial to consider the model's perspective. What information does it need to perform the task accurately? Examples of effective instructions often involve step-by-step guides or structured prompts that guide the model through the task logically. Once an instruction set is created, it's crucial to test and refine it. Conduct experiments to see how the model interprets and executes the instructions. Gather feedback and make necessary adjustments, aiming for instructions that consistently lead to the desired outcomes. The process of testing and refining is iterative, and continuous improvement is key to achieving optimal performance. Evaluating model performance after instruction tuning is essential to determine the effectiveness of your efforts. Start by establishing metrics for performance evaluation, such as accuracy, precision, recall, and F1 score, depending on the task. These metrics provide a quantitative measure of how well the model performs. It's important to perform baseline evaluations before tuning, serving as a comparison point for post-tuning results. This comparison helps highlight improvements in areas that still need refinement. In addition to quantitative assessments, qualitative evaluations are crucial. Analyze the model's outputs for consistency, relevance, and coherence. Tools like confusion matrices, ROC curves, and precision recall charts can aid in visualizing and interpreting performance data. When interpreting evaluation results, consider not just the numerical improvements but also the practical implications. An increase in accuracy might not be meaningful if it comes at the cost of significant computational resources. Aim for balanced improvements that enhance performance without compromising efficiency. Regular evaluation throughout the tuning process ensures that the model remains aligned with the desired outcomes.
When working with instruction tuning, you may encounter several common issues that can affect model performance. Identifying and addressing these issues promptly is crucial for maintaining effective tuning processes. Common problems include suboptimal model performance, misinterpretation of instructions, and setup errors. To solve performance issues, revisit your instruction sets and ensure they are clear and precise. Sometimes, models misinterpret instructions due to ambiguity or complexity. Simplifying instructions or providing additional context can alleviate this problem. Debugging setup errors often involves checking software dependencies and configurations. Ensure all libraries and packages are up to date and compatible. When encountering persistent issues, resources such as community forums, official documentation, and expert consultations can provide valuable assistance. Joining AI communities and engaging with others working on similar projects can also offer insights and solutions to common challenges. Remember, troubleshooting is a normal part of the instruction tuning process. Approach each issue methodically, and you'll be able to find solutions and continue improving your model's performance. Scaling instruction tuning for large datasets presents unique challenges but is essential for broader and more effective model applications. As datasets grow, so do the computational and resource demands. Efficient scaling techniques are necessary to handle this increase without compromising model performance. One approach to scaling is data partitioning, where the dataset is divided into manageable chunks, allowing for parallel processing. This technique not only speeds up the tuning process but also reduces the strain on computational resources. Balancing performance and resource use is critical. Implement strategies that optimize algorithm efficiency, such as using more sophisticated sampling methods or leveraging transfer learning to minimize the need for extensive retraining. Tools like distributed computing frameworks and cloud services can provide the necessary infrastructure for handling big data. These tools offer scalable solutions that adapt to your workload, ensuring efficient processing. Case studies of successful scaling often involve innovative solutions tailored to specific needs, such as optimizing data pipelines or employing advanced data compression techniques. By studying these examples, you can gain insights into effective scaling strategies for your projects. The field of instruction tuning is rapidly evolving, with several emerging trends and advancements shaping its future. As AI continues to advance, the demand for more sophisticated instruction tuning techniques grows. Emerging trends include the integration of machine learning with human-in-the-loop systems, allowing models to learn more effectively from human feedback and adapt to complex tasks. Innovative technologies such as reinforcement learning and meta-learning are also finding applications in instruction tuning, enabling models to learn how to learn, further enhancing their adaptability. Potential research areas include developing more efficient algorithms for instruction tuning, exploring the use of synthetic data for training, and creating more intuitive user interfaces for crafting instruction sets. These advancements have a significant impact on AI development, offering the potential for more intelligent, responsive, and versatile AI systems. Preparing for future challenges involves staying informed about these trends and actively participating in research and development. By embracing new technologies and methodologies, you can contribute to the ongoing evolution of instruction tuning and its applications in AI. As we conclude our exploration of mastering instruction tuning with FLAN T0, let's recap the key insights we've gained. Instruction tuning is a powerful technique for enhancing AI model performance by refining task instructions. The FLAN T0 architecture offers a robust framework for executing this tuning process efficiently. Throughout this video, we've covered the setup and execution of instruction tuning, the creation of effective instruction sets, and the evaluation of model performance improvements. We've also addressed common troubleshooting issues and discussed strategies for scaling tuning processes for large datasets. The skills you've acquired today will empower you to implement instruction tuning effectively in your AI projects. We encourage you to apply this knowledge, experiment with different approaches, and contribute to the growing field of AI. Your feedback and continued learning are invaluable as we collectively push the boundaries of what's possible with instruction tuning. Thank you for joining us, and we look forward to seeing the innovative applications you develop.